Hey there, welcome back to Mathematics for Electronics. And today what we're going to be talking about is Chapter 24 and Chapter 25. Chapter 24 is Vectors and Phasors, and Chapter 25 is the Mathematics of Phasors. And these two chapters you're going to find go hand in hand, so that's why we're going to cover them back to back, and you'll see how they nicely flow into each other. Basically, you could think of Chapter 24 as not only introducing you to, of course, vectors and phasors, but then you actually do get into adding phasors. In other words, one type of math, part of the mathematics for phasors. And then when you get in Chapter 25, you continue more adding and then subtracting, multiplying, dividing, and raising phasors to powers. So that kind of finishes up our semester. So I'm really glad to see you made it this far. Let's continue the fun. All right. So first thing we're going to talk about is what the heck is the difference between scalar quantities versus vector quantities versus phasors. And this is the big difference, right? Basically, I'm going to go ahead and just do a little visual for you. Pretend this is a perfectly horizontal line segment. And let's say this line segment was 7 meters long. So in other words, a scalar value has what's called magnitude, right? Magnitude. All right, pretty straightforward. That's a scalar quantity. Anytime you just are given some sort of a length, be it meters or inches or whatever type of unit, if it's a magnitude, you've got yourself a scalar quantity. And then once you take that same scalar quantity, but notice the difference. So now I'm going to say, yep, we do have a fixed point, just like with the scalar, but notice the other end is not a fixed point. Instead, it's an arrow. So what we have here is not only magnitude, but we have direction. So this could be 7 meters per second, and then the idea is, right, so it's going in this direction. And so if you can kind of wrap your mind around the idea that, yes, we definitely have magnitude. But what's important to understand is with vector quantities, we also have direction. All right, so notice scalar, just magnitude, vectors, magnitude, and direction. Right, simply by popping a little arrow at the end to indicate what direction, okay? And then last but not least, we've got ourselves a phasor. And this is what's fun about a phasor. Yes, you've got magnitude, you've got direction, but then you also have movement in that you are rotating your phasor, all right? So whatever the magnitude is, whatever the direction, now it's moving. So basically, a phasor is simply a vector that is rotating. And then what's important is that you've got to stop that phasor so that you can analyze what is the magnitude and direction of that phasor. In other words, a vector that is rotating and then stopped for analysis. All right. So notice the relationship, right? So scalar, just magnitude, vectors, magnitude and direction, phasors, you've got definitely magnitude, direction, but now you have movement, all right? So we're rotating it. So then the next thing that you want to think about is that, okay, if we're rotating this vector, then we're going to have to bring in this idea of imaginary numbers. Why the heck would we bring in imaginary numbers? Even the name imaginary number sounds kind of interesting, right? Well, first off, let me show you where they live. Right, so we have the real axis where we have positive reals, negative reals. We have the imaginary axis where we have positive imaginary, negative imaginary, and I'm going to go ahead and just draw out our very first phasor, All right, and let's say the magnitude of this phasor is 2. All right, so if we want to take this phasor and we want to rotate it 90 degrees, all right, so recall back to past chapters where we looked at that square, right, that innocent square, that means 90 degrees. So we rotate our phasor 90 degrees. And here we find ourselves on our 2J, right? So notice, right, our magnitude, right, except now it's on the J, or the imaginary axis. And if we rotate our phasor yet another 90 degrees, all right, now we're -2. Notice we've made it to the negative part of our real axis. Right, so from our original point, we've basically rotated it. What's 90 plus 90? 180, right? 180 degrees. So notice we are back to our real number, except it's negative. And if we continue the fun, all right, let's rotate it another 90 degrees. Now we have a -2J. Notice the magnitude is the same, right? We're simply rotating it. So yet another 90 degrees, or 90 plus 90 plus 90, that's going to be your 270, right? And so now we are back to our imaginary number, but negative. And then last but not least, if we rotate it yet another 90 degrees for a full 360, we're back to our positive real number. Now let's think about this in terms of math. In other words, this concept of an imaginary number. Right? Remember I said that we needed to consider imaginary numbers if we were going to start trying to rotate, right, our phasor. Right? In other words, it's a vector that's been rotated, that's our phasor. So if we want to have some movement, right, of our particular phasor here, we need to bring in an imaginary number. So what the heck is an imaginary number? It's basically, mathematically, no kidding, it's the square root of -1. This is full on the value. In the world of physics and math, typically you'll see a little I representing an imaginary number. In other words, the square root of -1. But in the world of electronics, what the heck does little I mean? Right? Little I in the world of electronics is instantaneous current, right? So in the electronics, right, this is instantaneous current. Remember in our formula for Ohm's law, right? I represents current or intensity of electron flow. And anytime you have a lowercase letter of whatever that quantity is that you're measuring, that means at that instant in time, right? So here you've got your clock watch and you're measuring the current around your circuit. Stop the clock. What is that current? Oh, it's 7 milliamps. Bam, that's instantaneous current. So therefore, in electronics, right, in the world of electronics, we can't use little I to represent imaginary numbers. Instead, what we use is a little j. All right? That's why for our vertical axis, we're using little j, right? Positive j to represent positive imaginary numbers, negative j to represent negative imaginary numbers. Okay, so this is an imaginary number in the world of electronics. So don't get confused if you crack open a physics book and you're like, hey, they're using little I. That's because, right, in other types of disciplines, of course, little I means imaginary numbers. That's fine. But in electronics, it's little j. All right, so let's go ahead and just play around with just some, just a little bit of just mathematical kind of concepts here just to wrap your brain around the idea of imaginary numbers, because of course chapter 24 you're getting introduced to this, right? So you have the square root of negative 64. Make that look a little nicer. All right, so if I were to rewrite the square root of negative 64, I could rewrite this as the square root of negative 1 times the square root of 64. All right, what is the square root of negative 1? Hello, all right, it's right here. All right, it's your imaginary number. What's the square root of 64? 8. And by the way, you could represent your imaginary number as J8 or, right, it's the same thing as 8J. Okay, just so you know, you can swap those around. But typically in your textbook, you'll see the J first. But, you know, understand that as long as you see a J in there, you have got yourself an imaginary number. Okay, so now let's go back to our groovy little example here. All right, so we can kind of understand, you know, how this works. Okay, so here, right, we have our magnitude of 2. Okay, so there's 2. It's a real number. How do you know this is a real number? No J. All right, so the magnitude of this is 2. All right, now what I'm going to do is use my rotating operator. What do you mean rotating operator? That's my imaginary number, all right? J is my rotating operator. If you ever read that or hear someone talking about that, that's what this means, right? Your imaginary number is what rotates your phasor, right? Remember, that's what the definition of a phasor was, right? Vector that's rotating, and then you stop it for analysis. So here we go. We're going to take our real number and we're going to multiply it by a rotating operator. In other words, we're going to multiply it by J. All right, so 2 times J is 2J or J2, right? Same thing. Okay. Now we have what's called an imaginary number, and take a look. There we go, right? This is it, right? 2J, J2, all the same, right? So don't get mixed up about that. As long as you sing J in there, you know you've got an imaginary number. Now let's take this imaginary number and again multiply it by our rotating operator. Okay, in other words, now we've got 2J and we're going to multiply it by J. All right, here's our 2J, multiply it by J. Well, let's ask ourselves mathematically, what does J equate to, right? What is that? 2 times the square root of what? Negative 1 times square root of negative 1. Very good. And then, what's the square root of negative 1 times the square root of negative 1? You got it, negative 1. So it's going to be 2 times a negative 1, which happens to be negative 2. In other words, notice your J's go away. If the J goes away, no J, what kind of number do you have here? It's a real number, all right? This is a real number, it just happens to be negative. All right, so here we are. All right, multiply that imaginary number. You rotated, all right, your phasor yet another 90 degrees, all right, with our rotational operator known as the imaginary number J, right, square root of negative 1. So 2J times J gets you negative 2. Now we want to rotate our negative real number yet another 90 degrees. So let's do it. So we have a negative 2 times J. That's going to get us negative 2J, which again, feel comfortable to write it either way, it's the same thing. In other words, by multiplying a real negative number by our rotating operator, which is square root of negative 1, all right, that's J, you end up with what kind of number? If you see a J in it, what is it? Imaginary, okay? This is a big part of chapter 24. Chapter 24 is going to ask you to identify quantities, and it's going to ask you to identify, is this a real number or is this imaginary? is this a real number or is this imaginary? And all you have to worry about is if you see a J, then yeah, baby, you've got yourself here. Basically, it's a negative imaginary number, right? That's what this is. As soon as you see a J, that's what you've got. Whereas here, no J, so you know you've got yourself here a negative real number. Make sure you're starting to pick up the difference. Very important. Okay, this is a big part of chapter 24. It's just identifying, what kind of number is this? All right, so now here we are. Right, let's go back to our axis, right? This is our, basically you're going to see soon that this is our complex number plane, okay? And so here we are back on this plane, and we are now in the negative imaginary, right, axis, and we're going to again rotate our phasor another 90 degrees, all right? And when we do that, we've got a negative 2j, negative 2j, and we're going to multiply it by j. So let's see how this math works, just to make sure you're really clear. So remember, j is simply the square root of negative 1 times square root of negative 1. So now we have a negative 2 times negative square root of 1 times the negative square root of 1 gets you negative 1, right? And then, of course, 2 negatives get you a positive. So we are back to 2. In other words, we are back to what we started off with. This is our positive real number. Okay? Real important to make sure you know the difference. Okay? If you're given 2, no worries. That's a real number. If you're given negative 2j, no worries, that's a negative imaginary number. As soon as you see the j, you know you're talking imaginary. As soon as you see the no j, right, you're talking about a real number. And then, right, the fun never ends in this class. What happens if you add a real number to an imaginary number? You get what's called a complex number. All right, complex number. All right, a complex number by definition is simply the sum of any real number and any imaginary number. All right, so make sure you can identify that. Again, a big part of chapter 24. You'll be given real numbers added to imaginary numbers, and you'll be asked, is this, in other words, is 2 plus j2 a real number or an imaginary number or a complex number? No worries. You see that you are simply adding a real and an imaginary. Bam, there's your answer. All right, you know you're talking complex. And now let's go ahead and just look at some of the fun things that you're going to be doing with a complex number. Slide right over here. Right, for example, you'll be asked to write it in basically the complex number form. So I'm going to go ahead and just give you an example. Typical problem right out of your chapter 24 exam prep problems, right? Given negative 3 plus square root of negative 36, right? Your directions are simply to write as a complex number. These would be your directions. All right. So what are you going to do? You're going to say, okay, well, there's my negative 3. What kind of number is that? No J means real, right? So you got your real number, and then now you have your negative square root of a negative 36. That's going to be square root of a negative 1 times the square root of 36. Bring on down your negative 3 plus, what is the square root of negative 1? Could it be a J? Yes. Square root of 36 nicely works out to be 6. And there's your final answer, right? Typical problem from chapter 24, right? You'll simply be asked to write whatever they give you as a complex number. Negative 3 plus J6 would be your final answer. All right. How would you write negative 25. All right, negative 25. Could you write it as a complex number? Negative 25. Negative 25 is what? No J means it's a real number, but notice that you could write it in the complex form, in other words, a complex number form, which would be negative 25 plus J what? 0. In other words, because you have a 0 multiplied by your J term means this definitely is a real number, right? Remember, it's a real number because why? You don't have this being multiplied by J, and notice it's not a complex number because you don't have an imaginary portion. I mean, that's the definition of a complex number, right? Is it's basically the sum of real and imaginary. But you can write this in a complex form. In other words, yes, this is a real number, but written in a complex number form. Okay, but it's important to understand that, yeah, this is still a real number, right? But you can write it in the complex number form. All right, what kind of number is this guy? Negative, right? So basically it's the square root of a negative 20. What is it? Imaginary, right? Now we could write this imaginary number in the complex number form as follows. In other words, 0 for your real plus J and then square root of 20. Right? Does that make sense? In other words, there's your 0 portion, right? So there is no 0 portion. Here's your imaginary portion. Therefore, it's 100% an imaginary number, but of course, written in that complex number form. How about negative 7 minus square root of negative 2? First off, let me bring this back. First off, let's go ahead and find out what kind of number is this? Right? This portion is what? If there's no J associated, right, it's your real, right? And then here we've got a minus. We can rewrite this as a square root of negative 1 times square root of 2. All right, I'll just continue to bring down my real number portion. All right, so that's going to be square root of negative 1, that's your J, times the square root of 2. What kind of number is this? You've got a real number, and you have imaginary. In other words, what you've got here is complex number. All right. All right, make sure you know how to do that. That's important. All right. Let's do another one. What about 0? Well, we'll just leave it as that, right? 0 is what kind of a number? And then I'd like you to write it as in the complex number form. All right, so let's think about that. So 0, we don't have J associated. We could put in a J portion, but no matter what, this is a real number. Does that make sense? Right? That's what we've got going here. Right? 0 is a real number. All right? It is real. Why? Because there is no J. As soon as basically this little coefficient becomes something other than 0, then you're talking either, complex, if you happen to have a real portion, or imaginary. Okay, if you have 0 here for your real. But 0 all on its own, you would actually consider it to be a real number, right? But this would be written in the complex number form. All right. Let's go ahead and do some plotting on our complex plane. This is basically the next step that we're going. So make sure that you know where our different complex numbers live, and actually where real numbers and imaginary numbers live. So here's our positive side of our real axis, negative side of our real axis, positive side. Notice what I'm doing here. I'm actually just introducing a q. Nothing magical about q. It's simply the coefficient, right? It's the coefficient in front of our imaginary number, right? And so, of course, this is going to be a negative jq. All right. We also are going to label our quadrants. So we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Always in this order. 1, 2, 3, 4. Okay, so let's go ahead and land some of these numbers and see if you can find their home, right? So 1, 2, 3, 4, 5, 6, 7. All right. So let's land this guy here, all right? So it's 1, 2, 3, 4, 5, 6, 7. And let's mark some stuff over here. And let's head on down 1, 2, 3, 4, 5. And mark some up here. 1, 2, 3, 4. All right. So we have a negative J1, negative J2, negative J3, negative J4, negative J5. Why? Because we're on the negative portion of our imaginary axis. And then, of course, we have J1, J2, J3, and J4 for the positive side, of course, of our imaginary axis. And then we have negative 1, negative 2, negative 3, negative 4, negative 5, and negative 6. All right, so let's see. We've got this point here. Let's go ahead and land a dot over here. Just pretend these are perfectly lined up. There's another little dot. We're going to determine how to express it. And let's see. There's another number, and let's come on down here. There we go. And all right, and let's see, let's make sure we get some fun over here in our third quadrant. And last but not least, let's see, we've got this guy. And let's come on out over here. All right. So what's important at this stage of the game is let's go ahead and basically figure out how would we describe these specific points on what's called our complex plane. All right. Clear a little room here. All right. So this is our complex plane. Home of complex numbers, along with, of course, real numbers and imaginary numbers. Right? This is our complex plane. All right. So first off, let's go ahead and determine how would we represent this dot. Notice where it is. Quadrant 1, all right? So if we're talking about the angle, right, that quadrant 1 covers, right, basically theta is going to be what? Greater than 0 degrees, right, but less than 90 degrees, all right? Quadrant 2, think about what this guy is, right? It's going to be greater than 90 degrees, but less than what? 180, right? That's the span that quadrant 2 covers. And of course, quadrant 3, right? Basically anything greater than 180 degrees, but less than 270 degrees. And then last but not least, bring this up just a hair. Theta, described in quadrant 4, is going to be greater than 270 degrees, but less than 360 degrees, which is also, of course, equivalent to 0 degrees, right? Remember, they're equivalent angles, right? This is 0 degrees, and it is 360 degrees. Remember, we talked about that a while back, all right? So just recall that. So this is the span of quadrant 4. All right, so in quadrant 1, take a look. We only have one little guy we need to determine the location. What's important to understand is the dot here on the positive portion of the real axis is not in quadrant 1. Why? This dot residing on the positive side of the real axis is exactly on the 0 degree line, right? Here it is, right? 0 degree line, exactly on, right? This is your 90 degrees, this is your 180, this is your 270. So it's really important to understand is that quadrant 1 covers everything just greater than 0 degrees. What's on your real axis is not in quadrant 1. In other words, complex numbers reside in these quadrants. That's so important to get, right? In quadrant 1, 2, 3, or 4. Right, complex numbers, the combination of real and imaginary, reside in one of these 4 quadrants. So if we look at this baby, right, we see that we've got a real portion, happens to be 6, and it's the sum of the real portion and notice the imaginary portion. So you just trace it back, right? That's going to be J2, right? This is what's called the rectangular form of, right, this complex number, right, which is located right here. So you could also think of this is the address, right? This is one type of address that gets you to this complex number, 6 plus J2. Okay, so I'm just going to put off to the side because you know everything we do builds in this class. So you want to make sure that you're making this connection. So this is called a rectangular form. It's the rectangular form of a complex number. Right? Complex number, we know by definition, is the sum of the real and imaginary. This particular complex form number is represented in what's called the rectangular form, where you simply have your real portion added to your imaginary. Let's continue the fun, right? And let's look at quadrant 2. In other words, this dot right here happens to be in quadrant 2, so we know it is a complex number, right? The direction is greater than 90, less than 180. In other words, it's in this realm, quadrant 2. And you would describe this as come on over here, a -4 plus J3. So again, this is the rectangular form of this complex number, which is -4 plus J3. Is this cool or what? All right, let's continue the fun. So now we're in quadrant 3. You got yourself another complex number. We need to figure out, well, what is one address that's going to get us there? Right? We want to get to this particular complex number. We can trace back what's the real portion. All right, that's going to be a -5. And then we can add it to the imaginary portion. That's minus J4. All right, so one address for this complex number is -5 minus J4. All right, that'll get you right here. This is the rectangular form of this complex number. And let's take a look at this guy. Now we're in quadrant 4. All right, so what is the rectangular form of this complex number? 1, 2. All right, so it's going to be 2 minus J5. All right, so now we have again a rectangular form of this complex number, which is simply the sum of the real portion, right, added to the imaginary portion. It just so happens that the imaginary portion is negative, hence negative J5. Yes, you could write 2 plus a negative J5, same thing, right? Your call. All right, so we covered all of the addresses for our complex numbers that live on the complex plane for this example. But notice we also have some other dots here, right? We've got a dot right here. This, of course, is on the positive real portion, right? So this is going to be a real number. How would we express it in rectangular form? We would say 4 plus J0. All right, does that make sense? Right? 4, there's your real portion. Add it to your imaginary portion, right? Which notice you don't have any, right? So therefore, this is a 100% real number, but written in the rectangular form, right? Where you have your real plus your imaginary. All right, so there's our positive real. Let's look over here. How would we express this particular number on a complex plane, right? In rectangular form, it would be -3 plus, let's see, J0. That's kind of a funky looking 3, but you get the idea. A -3 plus J0. In other words, there is no imaginary portion. This is a 100% real number. It just so happens to be a negative real number. All right, let's move on down here. So we've got another type of number. All right, well, actually I'm going to go ahead and add a little dot up here just so we can see both, right? So we've got positive versus negative. If we wanted to write the rectangular form of this particular number, this would be 0 plus J4, right? Just so you can see what that looks like. So this is 100% imaginary number. Notice it's not in quadrant 1, nor is it in quadrant 2. So it is not a complex number. You don't have even a tiny, tiny fraction of a real portion that's pulling this in either direction, right? It's right there straight up on your imaginary axis, and it happens to be positive. Versus if you wrote the rectangular form for this particular number, right, you would have 0 plus, let me keep it simple here, 0 minus J3, or of course you could also do 0 plus a negative J3. That's fine as well. All right, so this particular number, notice 100% what kind? Imaginary. Yes, imaginary, 100%. All right, so notice we have a 0 portion for the real, and then there's our imaginary portion. So notice it is not in any way, shape, or form being pulled into quadrant 3, nor is it being pulled into quadrant 4. If that were the case, then you would see some value here other than 0, right? It might be like 0.001, but it's something, right? If you see some sort of an effect, either in the negative or in the positive, then you've got yourself a complex number, and you would not be on the imaginary plane. So make sure you understand that difference, right? So we've got imaginary numbers, both positive, negative, real numbers, positive, negative, and then now let's go ahead and talk about, first off, a real-world example of a phasor, because you know when I'm talking about all these cool little dots, right, out here in the quadrant, and you know the various quadrants, either quadrant 1, quadrant 2, quadrant 3, or quadrant 4, okay, not only can we represent it, of course, with the J6 plus J2 rectangular form, but remember, this is a phasor. What do you mean a phasor? Let me go ahead and just to be a little cleaner, I'm going to go ahead and simply redraw my complex plane. Just imagine that it's perfectly straight. real axis and an imaginary axis. All right. But this is what's really cool, right? So here's our phasor, right? Here's our phasor. Remember we talked about this at the very beginning, right? So here's our phasor coming out of the origin, right? It has magnitude and has direction. And look at where it's going, right? It's going to some particular location on the complex plane. All right? So what's neat is not only can we express this complex number as, of course, rectangular form, but we can also express it in terms of another type of form, which is called polar form. But it's basically two sets of directions that get you to the same point. All right, it gets you to the same point. Let me kind of clean this up and put some numbers here so you can see it in action. All right, so there's that point we're getting to. All right. Do you recall way back in the not so distant future, if you had the length of one side and you had the length of another side, and it happened to be, take a look, what does that little square mean? Right triangle, right? So if you happen to have a right triangle, actually I'm going to make this a different value just so you really get it clear. So I'm going to use little r for, of course, right, we're on the real axis, and I'm going to use a little q just to simply represent the coefficient, right, of our imaginary axis. So if I wanted to solve for this guy, in other words, it's a side that is directly opposite my right angle, what theorem did we use way back in the not so distant past? Right? Was it something like Pythagorean's theorem? Right? Do you recall something like that? Where you took the other sides, for example, if this length was r, you square it, you add it to the length of this guy, which we're calling q for our little example, square it, and you do the square root, you're going to end up with the distance. Let me go ahead and label this appropriately. The distance from the origin to that point. What do you mean that point? Remember earlier we were coming up with the rectangular form. The rectangular form. I'm just going to go ahead and note that here. This is so awesome. Take a look. Rectangular form, right? This is the rectangular form of a complex number. But we know that if q is 0, we've got ourselves a real number. If r is 0, we've got ourselves an imaginary number. But if we have something for r and something for q, we've got ourselves a complex number, right? We're pretty comfortable now with understanding that difference, right? So now it's okay. One form we looked at was this idea of rectangular form, where you simply come out and you say, okay, how far out am I on the real axis? How far up am I on the imaginary axis? Bam, there's my rectangular form. But what's really cool is not only do we have what's called the rectangular form, but we have something called polar form, all right? And the polar form involves the distance from the origin to that point, which is rho, and now you've got yourself a groovy little formula to solve for that distance. Remember what a phasor is. A phasor has magnitude, that's your rho, and what else does a phasor have? Do you recall? Right? Think back. Right? I know it's been a while. Let's go back to what we first talked about. Scalar, only magnitude. Vector, magnitude and direction. Phasor, hello, you got the magnitude and direction. That's why, right, you're dealing with a vector. So you got the magnitude. All right, let's go ahead and bring it home, right? That's your rho, what we're talking about, right? and your direction. In other words, where is this puppy pointing? Right? Where is that pointing? And then we're going to rotate it. All right? So let's go back and see now for our particular problem. All right? So here we are. All right? There's our row. And now we just need direction. Take a look at what I'm using. Ooh, interesting. Theta. Where have we seen that before? Theta. Right? Remember when we had our quadrants labeled, right? So we have quadrant 1, quadrant 2. Remember, this doesn't change. Quadrant 3, it's always in this order, so make sure you understand the order, right? 1, 2, 3, and then last but not least, quadrant 4. All right? And it's within these quadrants that you actually care about that theta, right? All right, well, let's talk about the theta. What if I wanted to solve for that theta? What if I wanted to know what theta is for this particular problem? So now we're back to our SOHCAHTOA, right? SOHCAHTOA. Recall that? What is SO? Sine of theta is what? Opposite divided by hypotenuse. Yeah, baby, that's what we were solving here, right? Or we squared our real, added it to the square of the imaginary, took the square root, right? Pythagorean's theorem, right, shows us how to solve for that magnitude of the hypotenuse. So this row is the hypotenuse, okay? This cosine of theta is adjacent, right? So that's going to be our r, our real, divided by our hypotenuse. And then here we go. Our tangent of theta is what? Opposite, there's your O, divided by adjacent, which is your R. This is the key, right? This is how we're going to solve for theta if all we know is the real and imaginary portion of our number. This is it. All right, so let's play around, man. We got it. The tangent of theta is equivalent to opposite. What's opposite? Q. Divided by adjacent. What's adjacent to theta? Remember, it's not the hypotenuse. Yes, it's true, the hypotenuse is right adjacent to theta, but that's already taken, right? That's the hypotenuse, right? Hypotenuse is defined as the side opposite your 90 degrees. So you can't call this an adjacent side. This is the hypotenuse. But you can call R, or the real portion of your complex number, right? That's definitely adjacent, right, to your theta. So now let's go ahead and solve for theta. Remember how we did that, right? We broke into this function by doing the inverse tan of the tan of theta, right? Remember we did this in past chapters, right? And because this is an equation, what you do to one side of the equation, you must do to the other. So you also have to do the inverse tan of Q divided by R. The inverse tan of tan, out pops out pops theta. And then on this side, there's your formula, right? So theta is the inverse tan of Q divided by R. Now you are armed and dangerous, right? In other words, the rectangular form R plus JQ is equivalent to the polar form rho angle theta. So I'm going to go ahead and just put here polar form. So that's what this is, right? It's the polar form, right? And rho, we know, is simply the square root of r squared plus q squared. And then theta is simply the inverse tan of q divided by r. So now we have a way to represent any number in either rectangular form, r plus jq, or if we know the distance from the origin, that would be, of course, your rho, right, your magnitude. And then if you know the sides, right, you can do the inverse tan of q divided by r, and now you can figure out your theta. Okay, so two ways. Basically, think of this as two directions, two sets of directions that get you to the same point. If someone gives you the rectangular form, you get there. If someone gives you the polar form, you get to the same point. In other words, for this particular example, you'd get to quadrant 1 and you'd get to that dot. All right, so with that said, let's actually crank a few numbers out just so you can kind of see this all kind of pulling together. This is pretty awesome. All right, so what we're going to do is let's just do a little conversion here, and we'll just kind of see how we can go in between, right? So let's say we were given a negative 12 minus j18, a negative 12 minus j18, and we were asked to convert to the polar form. That's what we want, right? So in other words, go polar. All right, if that makes sense. This is the directions. Go polar. All right, how would you do that? First off, the idea is to understand that right now what we've got is the rectangular form where this is the real number and this is our imaginary number. All right, so the first thing you want to do is identify that. In other words, you got to know what's in the real portion. Ah, my real portion is negative 12. And then you have to identify, well, what's the imaginary portion? Ah, the imaginary portion is, don't forget the negative, negative 18. And now we're ready to go polar. In other words, the polar form is rho angle theta, or magnitude angle direction. Okay, and we know what R is and we know what Q is, so now it's plug and chug. All right, so solving for our magnitude, our rho, what are we going to do? We're going to say, yep, back to Pythagorean's theorem, right? We're going to say rho equals the square root of our r squared, right? Negative 12 squared plus q, negative 18 squared, right? And when you take negative 12, square it, and negative 18, square it, you work out 21.6. And then the next thing we want to figure out, what the heck is our direction, our theta? And we know that's going to be the inverse tan of Q divided by R. So that's going to be negative 18 divided by negative 12. All right, and then before we move on, let's just talk about one other thing. Okay, so here we have our groovy little formula for theta, right? The inverse tan of Q divided by R. Well, this is going to work perfectly if Q and R are both positive, right? Because that means we're in what quadrant? Right, we're in quadrant 1. But what happens if we're actually in quadrant 3? So let's just take a look at that. What if we were here? But it just so happens that the magnitude of our real number is a negative r, and the magnitude of our negative, the magnitude of our imaginary number is a negative jq, right? This would have been a positive jq. All right, so what is going to keep us from misidentifying? In other words, when we get to this formula, right, here we are, inverse tan of Q divided by R. If it's a negative Q divided by a negative R, right, a negative divided by a negative becomes a positive, right? And basically, we think that we're here, right? We think that we're in quadrant 1, but we're not. We should be in quadrant 3. So we need to figure out some way to adjust our theta formula so that we can basically, think of it as a correction factor, if that makes sense. All right, so in our correction factor, basically what we want to do is make sure that we either add or subtract 180, right? So for quadrant 3, of course, we're going to be subtracting 180. That way we're going to correct, right? If ever we are in quadrant 3 and we end up with a theta here, we want to make sure that we say, oh, no, actually we want to bring it back to quadrant 3. So this is really the direction that we're about, right? So we would subtract 180. Likewise, what if we were in quadrant 2? Let's do this example, right? What if we're in quadrant 2? So take a look, all right? So we've got here a negative real and a positive imaginary, right? If you go to that formula, right, this groovy little formula here, and you divide your negative, right? Actually, if you're in quadrant 2, it would be a positive q divided by a negative real, right? Positive q divided by negative real, you come up with a negative value, which looks a heck of a lot like what? If you were here, right? If you were in quadrant 4, right, here you've got your positive real, but you have a negative q, all right? If you jump on your inverse tan of, all right, your negative q divided by your positive r, you still get a negative value. So you could actually come out with a theta that is here, but you don't want it here, you actually want it here, all right? You want your theta to be for quadrant 2. So we also need to do a correction factor as well. Right here in quadrant 2, we're going to take theta and add it to 180. Notice no correction factors for quadrant 1 or for quadrant 4, right? Only for quadrant 3 and for quadrant 2, right? So I'm going to go ahead and just note that just over here. I'm going to put, right, just a little thing here of plus, right? So here we have theta, right, equals the inverse tan of q divided by r, plus 180 if we're in quadrant 2, and minus 180 if we're in which quadrant? Quadrant 3. Very good. Yep. Excellent. All right, so just a little correction factor, and that, of course, is going to make life really good here, because here we are, right? This is a typical problem that you're going to be playing around with in chapter 24 and 25, actually. We're actually moving into 25 right now. So mathematics of phasors, convert from rectangular to polar, right? What I recommend is just a quick and dirty, and I'm talking quick and dirty. It doesn't take you but a second, right? Draw yourself a quick and dirty complex plane. You know that's positive. You know that's negative. You know this is positive. You know this is negative. You've got a negative real, and you have a negative imaginary, so you know that you are in which quadrant? This rectangular form happens to be in quadrant 1, 2, 3. And if you're in quadrant 3, what the heck are you going to do with theta? Subtract 180. All right, subtract 180. That's important. All right, and so now let's go ahead and do that. All right, so you want to go ahead and calculate. All right, what is the inverse tan of negative 18 minus, or divided by a negative 12, and then you're going to do minus 180. Minus 180. Right? Go back. Right? Go back to this guy, right? This is your formula that you're playing around with. Remember, your correction factor is only if you're in quadrant 2, add 180. If you're in quadrant 3, let me make my quadrant 3 look more like a quadrant 3. There we go. So 1, 2, 3. Quadrant 3, minus 180. most definitely for this particular problem, all right, negative 12 minus J18, bam, right? You're in quadrant 3, negative 180. All right, and so if you work this out, all right, let's go ahead and do that, all right? And this is probably a good time to also verify. Notice I'm using 180. What's the units? Degrees, all right? That's important, right? Degrees. That means, right, I'm just going to put a little note here. Make sure your best friend, also known as your calculator, right, is talking whatever units you're about. In this case, degrees, right, is what we're getting ready to do. Okay, it's so important, right? Whatever the language, right, whatever the units, that's why I like to think of units as language, right? Whatever the units you're talking, right, make sure that you've got it going on. And so right now, if we're going to subtract 180 degrees, check and make sure your best friend is in fact doing that, right? So let's go ahead and come over here and verify that. So if you didn't know, if you have a TI-84, this is one way to check. So notice what I did. I clicked on mode directly, all right? And then if you come on down, do you see where it says radian and then notice degrees is highlighted, right? How you would change that, do you see the arrows here, right? If you click on the arrow, right? So you can bring the arrow, right, down, there's radians, and then you can bring it on over, and you simply hit enter to make sure it's in degrees, right? Let's say you wanted to convert it to radians, so then I'm highlighting radians, I hit enter, and then notice now degree is no longer bolded, radians is bolded. And so now I know that the language that my calculator is talking, my best friend right now, is in radians. But we don't want radians, right? Because we're going to subtract 180, which is degrees. If we were going to subtract, what is 180 equivalent to in radians? Pi, right? All right, so then of course if we're going to subtract pi, then we'd want to talk in radians. Make sure you know that. That's important. All right, so I'm going to go back to degrees. So notice you're just using your arrow over. Hit enter, and then you'll see how it's bolded differently. And then how do you quit your mode? Notice quit is in the blue, right? Your second, so second mode, and then it goes away. And now let's do the inverse tan. So notice inverse, there's your second, and then hit tan to get inverse tan. And, right, we're going to be doing negative 18 divided by negative 12, which is 18 divided by 12, however you want to, you know, move that. If you want to actually type in negative 18, that's fine. Divided by negative 12. It's the same thing as 18 divided by 12, of course. And then now we're going to do minus, y minus. Remember, what quadrant are we in? Quadrant 3. So minus 180. Come on back. 180. And then hit enter. All right. So now we have our angle, negative 123.69. What are the units? Degrees, right? If you set your mode for degrees, then of course your answer will be in degrees, right? You've changed the language, right? The language is now in degrees, so whatever you get spit out at you, of course, is in degrees. So we have a negative 123.69 degrees, all right? So theta is going to be negative 123.69 degrees. And then the idea is think about, does this make sense? Does this make sense? Right? Remember we talked about positive angles versus negative angles. All right? So what we're saying is the magnitude is 21.6. All right? And we're saying that, right, going this way, that's a negative 90. If you keep going, there's the additional. In other words, the negative, right, means you're going in this direction, your negative angle, so it's going to be negative 123.69 degrees, and of course your magnitude is going to be your 21.6. All right, there's your magnitude. So magnitude and direction, which is identical, right, to, of course, the rectangular form. You go out negative 12, right, and you come down a negative j18. All right, two sets of directions to get you to the same point on your complex number plane. So what you can say is a negative 12 minus j18 is equivalent to 21.6 angle negative 123.69 degrees. All right, so make sure you know how to do that. Basically, we're just going from rectangular to polar form. And then, of course, you want to make sure that you can go the other way. In other words, what if you were asked, instead of going from rectangular to polar, make sure you can go from polar to rectangular. Let's do an example of that. Right, so this time, right, we're given 4.09. Make my 4 look more like a 4 for you. 4. There we go. 4.09. Angle negative 70.2 degrees. And what we're asked to do is go rectangular. Go rectangular. Okay, so what we have here is, of course, rho, angle, theta. Right? This is all we know about our problem. Rho, angle, theta. And our goal is to get r plus jq. So then the question you need to be asking yourself is how could I solve for r if I only know rho and theta? How could I solve for q if I only know rho and theta? This is so awesome, right? Let's think back to our SOHCAHTOA, right? SOHCAHTOA, right? And our good old-fashioned, just super basic example. Here we are in what quadrant? Right, quadrant 1, right? Remember, this is quadrant 1. Have our very basic example. There's our r, there's our q, there's our theta, and there's our rho. And what we're saying is basically we're back a couple of chapters to where we were talking about right triangles, right? Talking about right triangles. And the idea that if you only know the hypotenuse, rho, and you only know the direction, theta, you can solve for r, and you can solve for q. All right, so the idea is, how would we do it? Okay, well, let's think about our trig functions that involve h, right? Remember, h is your hypotenuse, right? That is your rho, right? Rho is your hypotenuse. That's the side opposite your 90 degrees. Excellent. So now check this out. If you go to the sine of theta is equivalent to, there's your trig function, sine is equal to opposite. What's opposite of theta? Q divided by what? Hypotenuse. Hypotenuse is rho. Okay, and what we want to do is solve for q, right? Remember, we want q in terms of rho and theta. Take a look. We want q in terms of rho and theta, right? This is back to what I would say chapter 4, 5, right? The fundamentals of algebra. Remember we talked about that way, way back? Remember, I promised you that everything we learn in this class builds, right? So here we are in chapter 25, right? And what are we doing? We're talking about basic fundamentals of algebra. We want to solve for q. So how the heck do you solve for q? How do you do it? You're going to multiply both sides by rho, right? So that changes the denominator of q to 1. So q, in fact, is simply rho times the sine of theta. Yeah, baby. Take a look. Here it is, right? So there's your q, which is this guy, right? So you could literally rewrite this as j times rho times the sine of theta. Take a look, right? Pop q out, and in its place, there's your magnitude, 4.09 times the sine of negative 70.2 degrees. Now we just need to solve for r, right? So r, notice, what relationship is r to theta? It's adjacent. Excellent. So that means we're going to pull out our cosine function. The cosine of theta is equivalent to the adjacent side, that's your r, divided by the hypotenuse, that's your rho. Now we're back to chapter 4 and 5, Algebra Fundamentals. Solve for r. What are you going to do? Multiply both sides of the equation by rho. That's straightforward. All right, both sides by rho. And now what you got going on, right, is basically r is equivalent to rho times the cosine of theta. Right, and that's what you put right here. Right? In other words, pull r out, and in its place you're going to substitute rho times the cosine of theta. All right. Let me make this a little more simple too. Right, so rho times the sine of theta, and that's your q, and then rho times the cosine of theta, that's of course your r. So armed with that information, let's go ahead and solve for this particular problem. We want to go rectangular, all right? So let's plug and chug, all right? So we want to figure out, well, what the heck is r for this problem, all right? So r is going to be rho 4.09 times the cosine of negative 70.2 degrees. Notice you've got to get your best friend, also known as your calculator, to be talking degrees before you crunch this out, right? So make sure you make that change. And once you make that change and you multiply 4.09 times the cosine of negative 70.2 degrees, you should get 1.39 for your real. Now let's go ahead and work on the imaginary portion, right? That's going to be q, and q is going to be rho times the sine of theta. All right, rho again, 4.09 times the sine of negative 70.2 degrees. And when you work that out, all right, make this not so squished in here, there we go. All right, you end up with q being 4.9 times the sine of negative 70.2 degrees. Again, make sure that your best friend is in degrees. And when you crank that out, you should get something around negative 3.85. Right, so now we know our r, and we know our q. So it's a matter of bringing it together in our rectangular form, right, which is going to be 1.39 minus 3 point. Actually, let me go ahead and not forget the j, very important, j 3.85. All right, so the big takeaway here is that 4.09 angle negative 70.2 degrees will get you to the same location as 1.39 minus 3.85. Two sets of directions, right? It's so important to understand this. Two sets of directions that get you to the same point on your complex plane. All right? Two sets of directions get you to the same point. By the way, what quadrant are we in? Just out of idle curiosity. Just think about that. All right? So we've got, remember, there's your real, your negative real, your positive imaginary, your negative imaginary. All right? So here's our positive real and our negative, right, imaginary, so it would be somewhere out here, which is the same as our magnitude 4.09. And notice, right, if it's negative, you're going to be going in this direction for a negative angle. Actually, didn't make it very accurate, but you get the idea. All right, so just, right, you know this is 90, so maybe come down something like maybe this. All right, so if you come on, right, there's your negative 70.2 degrees. All right, so we are in quadrant what? What quadrant are we in? 1, 2, 3, 4. Quadrant 4. Quadrant 4 has positive reals, negative imaginaries, right? And of course, there's your magnitude 4.09 and your direction. Because it's a negative, you're going to go in this direction. Remember, negative angles. So there's your negative 70.2 degrees. All right? 2 sets of directions, polar form, rectangular form, that get you to the same point, right? No matter what, you end up in the same point in the same quadrant. All right. So now that we are armed and dangerous, but in a good way, right? Dangerous in a good way. We are ready now to look at all the different ways that we can play with phasors, right? Remember the very beginning, looking at scalar, vector, and phasors? Now it's all about phasors, but specifically the mathematics of phasors. All right, we've been looking at going between polar and rectangular, and now let's look at if ever you wanted to, add. All right, so I'm just going to put adding or subtracting phasors. Because most certainly this is some fun things that we're going to be doing. What you're going to want to do is go rectangular. All right? Go rectangular. You're going to want to do that first. Versus, I'm just going to kind of give you the bird's eye view of everything. If ever you want to multiply, right, so I'm just going to go ahead and put in here multiplying phasors. If you're multiplying phasors, believe it or not, you want to go polar. That's your first step. All right, as a matter of fact, I'll even put this. So this is our first step. And we'll do little examples kind of going down each of these columns. So we have adding and subtracting phasors, go rectangular. Multiplying phasors, go polar. If ever you would like to divide, right? So dividing phasors. Go polar. All right. That's going to be our first step whenever we divide. Go polar. And then the last but not least little example we're going to be doing for today's fun is we're going to be raising phasors to a power. And first step, go polar. All right. So this is real important, right? Real important is that, matter of fact, I'm going to just off to the side. Well, actually, let me just do it just underneath so we'll have plenty of room. All right, so in other words, just to remind you, what do you mean polar? That's polar, right? Go polar. Dividing phasors. First step, go polar. All right, this is what you're about. This is your first step. Multiplying phasors. You want to go polar. And the only time where you're like, you know what, I got to think about that other type of form, R plus JQ, that's the rectangular form. All right, so this is just to kind of remind you. When I say go rectangular, what do you mean? Oh, we got to get in the R plus JQ form. That's important. All right, so let's do some examples. And we'll do examples of each one. All right, each one. All right, let's go ahead and add 3.8. Let's see, make my 3's look a little better. So let me see. Example, I'll just do that. Example. All right, we're going to add 3.8 angle 75 degrees and 1 plus J 1.8. All right, so that's going to be our example, adding and subtracting phasors. So these are our two phasors, and we want to go rectangular. Note, we're set with this guy, all right? We don't need to do anything. We only need to convert this guy, in other words, our very first phasor, to rectangular. Because what's important is both of them are in rectangular form before you can then add or subtract, all right? But for this example, we'll add. All right, so we want to convert our first phasor to rectangular. So we're going to take our rho, that's our 3.8, times the cosine of 75 degrees, add that to J, 3.8, times the sine of 75 degrees. And that works out to be 0.98. All right, so that's 3.8 times the cosine of 75 plus J, 3.67. That's again 3.8 times the sine of 75 degrees. All right. Our second step, in fact, let me do here. All right. So our second step, right after we went rectangular, so now we have our phasor, our first phasor represented rectangular, and of course our second one was given. Second step in this process is to add reals and add imaginaries. Could even break this up so it's super obvious, right? So let's make sure you catch every step. So add reals. Third step, I'll say add imaginaries. Imaginaries, that's basically the imaginary terms, right? And then fourth step, combine for final answer, right? Combine for final answer. All right, so add reals. What do you mean add reals, right? There's your 0.98, right? And you're going to add that to 1, all right? And when you add this real portion to this real portion, right, you come up with, of course, 1.98. Add imaginaries. So your imaginary portion, that's your J, 3.67. Add that to this imaginary portion, J, 1.8. When you add these puppies up, you get a J, 5.47. And then combine for final answer. Combine for final answer, right? That simply means there's your real version, or your real portion, right, 1.98. And you're going to add that to J, 5.47. And you're done. This is it. This is your combo, all right? And your final result, right? So if you're asked to add 3.8 angle 75 to 1 plus J 1.8, there it is, okay? Of course, don't be surprised if I, on an exam, ask you then to express your final answer in what form? If automatically you're going to get rectangular form, you know I'm probably going to ask you to convert or go polar for your final answer. So just be prepared. And you know how to do that, right? You know how to go between rectangular, polar, or polar rectangular. And so just bring back, go back to the basics and make sure, you're comfortable doing that. But of course, if you know how to do the mathematics of phasors, you will be comfortable. For example, here we are with our next example, right? Multiplying phasors. Right, so multiplying phasors, go polar, your very first step. All right, so let's go ahead and look at an example. What if you were asked to multiply? So here's our example. I'll just put example, right, multiply -3 angle 150 degrees and 4 minus J3. Okay, first step, go polar. All right, so here's your example. Multiply -3 angle 150 degrees. Hey, you're already in polar form. You're good. And 4 minus J3. Oh, got to go polar. Okay, so it's similar to if on an exam, right, I asked you to add those two phasors and then final answer in polar, you'd have to go polar, right? So you're going to know how to do this anyways. Just giving you more practice. So here we go, right? We want to convert basically convert the rectangular form of this to polar. So think about how we would do that, right? So we're going polar. So rho is going to be, of course, the square root of r squared. That's going to be 4 squared plus -3 squared, right? And when you work that out, you end up with 5. And theta is going to be the inverse tan of q divided by r. That's a -3 divided by 4. Remember, don't forget the sign, real important. All right, so it's a -3 for your q divided by r. And then what's the other question you've got to ask yourself? Just a quick and dirty, right? You can do it right here and say, what quadrant am I in? So I've got a +4 and I have a -J3. Bam. I'm in quadrant 4. So do you need to add or subtract 180? No. So the inverse tan of -3 divided by 4, whatever that is theta. That works out to be -36.87 degrees. Again, it works out in this if your best friend is in what language? Degrees, right? So make sure, right? Make sure you're talking degrees. And so now you've got your -3 angle 150, and now you've converted this guy. So your final answer, of course, here, 5 angle -36.87. Okay, so you've gone polar. That's your first step. All right, and now let's do our second step. Second step, whenever you're multiplying phasors, okay, is basically you're going to multiply the magnitudes, right? So multiply magnitudes. Remember, that's your rows. And third step, you're going to add your thetas, right, or add directions. And then last but not least, combine for final answer. Just like our last problem, right? Combine for final answer. All right, so multiply magnitudes. Basically, right, we've got a -3, right? We want to multiply it by 5, right? Our new problem is basically, because we've converted our rectangular form to 5 angle -36.87, so now we have two polar forms, and we're ready to rock and roll. So the magnitude's -3 times 5. All right, so it's going to be -3 times 5, which is a -15. And then we're going to add our directions. All right, so basically what we're going to do from our original example, +150. So 150 degrees, and we're going to add that to a -36.87 degrees. When we add those up, we end up with a +113.1 degrees. And combine for final answer, right? Final answer is going to be a -15 angle 113.1 degrees. You're done. All right, this is how you multiply phasors. All right. And now let's go ahead and look at, well, what if we want to divide phasors? What's the first step? There it is. Go polar. All right, go polar. That's our first step. All right, so let's go ahead and do an example. All right, let's say we were asked to divide, right, these values, right? Divide 15 angle 10 degrees by 3 angle -30 degrees. Okay, Now, real important to understand here is getting the verbiage, right? Typical problem in your book, right? You may not see the actual setup of numerator divided by denominator, but understand the verbiage. So it's saying divide, so you know you are doing some sort of division, and it's 15 angle 10 degrees by 3 angle negative 30 degrees. All right? I always have students that get that mixed up. Don't let that be you. By means whatever's following it, that's what goes into whatever you started. So 15 angle 10 degrees divided by 3 angle negative 30 degrees. What form are both of these phasors in? Polar, all right? They both are in polar form. Notice, dividing phasors, what's your first step? Go polar. So some problems you may be ready to go, right? Some problems you may actually have, what you need to move ahead, right? So don't feel like you're always going to be having to convert, but be ready, all right? Just be ready, because you could, okay? But for this particular problem, right, you've got two forms, right, that are identical, right? It's what you want. So then the second step, right, after you go polar, right, remember that was your first step, go polar, and it just so happens that the problem was already there, right? There you have it. So second step says now what you're going to want to do is divide, right, numerator, or I'll just put divide magnitudes. So I think it's pretty obvious. The idea of when you say divide magnitudes, divide the numerator by the denominator, right? Third step, now this is important, subtract. Subtract your directions, right? Subtract your angles. Right? I'm calling them directions because I'm trying to make sure you keep in the back of your mind this idea of what a phasor is, right? There's magnitude and direction. So you're going to subtract the directions. And then the last step, whenever you're dividing phasors, is you combine for your final answer. Yeah, baby. All right. So let's work with this one. Typical problem from, we are basically in chapter 25 if you haven't figured that out yet. So typical problem from chapter 25. This is your mathematics of phasors section. So divide magnitudes, that's going to be 15 divided by 3, which is of course 5. Subtract your directions, right? It's also important to understand you're subtracting what from what. It's your, basically your numerator, right? You're going to take the denominator away, if that makes sense to you. So you're subtracting the denominator or the bottom phasor from your numerator, okay? Subtract directions, right? So whatever this is, you're taking it away from that. So watch your signs. So 10 degrees minus, and then take a look, it's a negative 30. So that's where you're going to do your plus a positive, right? And then, let's see, too happy with my parentheses. There we go. All right, so that's going to be, of course, 40 degrees. Scoot that over. All right, so combine for final answer. So your final answer is going to be a magnitude of 5 angle 40 degrees. That's what happens if you divide 15 angle 10 by 3 angle negative 30. All right? All right, another way to think about it, a lot of students like to do this. In other words, I'll just say there's your magnitude and then the angle, 10 degrees minus negative 30 degrees. All right, and of course, ends up being just what we came up with, 40 degrees. Cool? All right, same idea. Okay, all right, and then now for final little fun we've got here with our phasors, we're going to raise phasors to a power. All right, raise phasors to a power. First step, make sure that you go polar. That's important. All right, and I'm just going to go ahead and note the steps here just so you can see them, and then we'll do a problem. Second step is you're going to raise your magnitude to a power. So whatever the magnitude is, that's your row. You're raising it to the power given. Third step, you're going to multiply your angle or your direction, right? Multiply direction by power. Right? That's important to understand. So you're multiplying whatever that theta is by the power. And then fourth and final, right, you're going to combine for your final answer. Combine for final answer. All right, so let's do a problem so you can see this in action. All right, what if I gave you this? 526.7 angle 2.95. Do you remember what that cute little superscript r is? That's radians, right? And we want to take this phasor and we want to raise it to the 1/3 power. 1/3 power. Make that look a little more readable there. Yeah, 1/3 power. Basically, this is the same thing as what? Right? I'm asking you to do what? Just going to rewrite it under here so you can see. Basically, I'm asking you to find the cube root. All right, that's what that means. Remember, we, again, blast from the past, right? Fractional exponent, right? Fractional power. That, right, is a direct link to the idea of some sort of a root. In this case, right, there's not a 2 under here. This would be a square root. There's a 3, so this is a cube root. So 5.26.7 angle 2.95 radians, raising that to the 1/3 power is the same thing as if I said take the cube root of 526.7 angle 2.95 radians, right? It's the same thing. Okay, so on an exam, if you find yourself with this kind of a problem, simply convert it to a fractional exponent, and now you're rocking, right? Raising phasors to a power. All right, so let's continue. So how would we solve this? All right, so first thing we're going to do is let's go ahead. I'm just going to move this up a little bit. All right, we're going to raise the magnitude to a power. So the magnitude, all right, that's going to be 526. All right, so let's go ahead and do that. 526.7, and I'm going to raise that to the 1/3 power. All right. There we go. And then I'm going to take the direction, that's 2.95 radians, and I'm going to multiply by 1/3. All right. So when you take 526.7 and raise it to the 1/3, all right, you get 8.075, and your angle or your direction, 2.95 times 1/3, that gets you 0.983 radians. And this is your final answer. It's that simple. All right, it's that simple. You can do this, right? Just work through your, exam prep problems. Ask questions. You can do this, all right? Don't let this wig you out. This is basically finishes our semester, and this finishes chapter 25, right? Chapter 25, you'll be adding, subtracting phasors, multiplying, dividing phasors, and you'll finish it off with raising phasors to a power, which if it's a fractional power, now you know, oh yeah, I remember, that's that crazy root, right? Either square root, cube root, whatever. All right, you can do this. And of course, don't be surprised if your final answer, for example, in this case, for our raising of a phasor, right, that was a polar form, don't be surprised if on an exam I ask for the rectangular form. No worries, you can do this. You know the relationship between rectangular form and polar form. All right, so have fun with this. Get study groups together, help each other out, blast the whole class an email with your questions. I'll get it, of course, and so will the rest of your colleagues in the class. And on your end, if you're blasted with an email question from another colleague, please, help them out. Okay, this might be simple to you, but someone else in the class might be like, ooh, hey, can I get your perspective? And help them out. So study groups are great, helping each other via email, whatever works. Get on those virtual chat rooms, work out all these groovy problems that you see. Invite me if you want. I can definitely help out. It's all good. All right? Have fun with this. And realize that this is the basis of talk about cool electronic stuff. All right? What you are learning, this idea of the mathematics of phasors, I mean, it's incredible. You are now opening the door to generating sine waves. And then now, if you think about it, remember what a phasor is. It's a vector that's been rotated, and then you stop. Well, what happens? Let's see if I can make this, right? If let's say this is your vector, right? Magnitude, direction, right? And now we're rotating it, right? It's no longer a vector. It's a what? Phasor, right? Well, if somehow I could magically highlight the end point of this pen, and so if you could plot where the end point of this pen is as it's rotating, guess what you are creating? Sine wave. That's what's going on, right? As this right phasor is rotating, boom, 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 boom. Because remember, not only is it rotating, it's moving, right? So it's moving over time. So there's a lot of cool things going on, right? It's moving over time, it's rotating, and so if you can follow the end point of that phasor, you are plotting a sine wave from negative infinity to positive infinity, right? It's just, and so that's awesome because now when you get into your DC AC classes, okay, DC flat line, not so interesting with phasors, excuse me, but AC, hello, alternating current, alternating voltages, right? We're all about, right, we're all about rotating phasors, okay? So you're going to be able to solve for currents, voltages. I mean, it's amazing. You'll be given circuits where sometimes your current may be in polar form or rectangular form. You'll be given voltages around your series parallel circuits that are in polar or rectangular form. And then depending upon the formula, right, if you want to, let's say, calculate the total voltage drop in your circuit, so you have to add V1 to V2 to V3 to V4 to however many voltage drops you've got in your circuit. You're adding, so what kind of form for our complex number are we going to need if we're adding? Oh, that is rectangular. There you go. Okay, now we need to solve current. We need to solve for total current using what law? Ohm's law. All right, so let's say we're using Ohm's law, total current. We know the voltage source, and we know the total resistance. All right, think about Ohm's law, right? V equals IR. All right, V equals I when I say IR. V equals I times R. So if you want to solve for I, what are you going to do? Divide both sides by R. So you're dividing. Oh man, so I'm dividing complex numbers. So that means what kind of form? Dividing, go polar. There you go. So now you need to make sure you have your voltage source, polar form, make sure your total resistance, polar, then you can divide and bam, now you've got your current, right? So everything you're doing here, what's so cool about this Math for Electronics class is it is math for the real world. That's what electronics is all about. It is the real world. So I'm excited for you, and I hope you're excited too, because you're going to keep your A if you keep on with these problems, complete those textbook exercises, study groups, awesome, right? Keep the communication between me and you and with the rest of the class, and you'll do fine. And then you'll have lots of fun as you move on to your higher level courses, where everything you learn here, you get to apply, right? And much more of the real world. So have fun and take care.